So I'm Stewart, and thank you all for having me here. I've been working with Xen on Arm for 8 years, and I've been with AMD for the last 2 years. This is my first in-person Xen summit. So like I said, primarily working with Xen on Arm, and I want to talk to you today about how we're using Xen VPCI with PCI pass-through on ARM and on x86 a little bit, but I'm approaching this from the ARM side. But both ARM and x86 use some common code, which is called VPCI. I want to start by saying, I'm newer to the VPCI game, so I'm building on the work of many others. So I want to just thank everyone who has been, involved in this VPCI journey, including, the many contributors, maintainers, and reviewers, and you all know who you are. So thank you, everyone here, and who is also not here. So. I'm going to assume there's a little bit of general basic PCI knowledge with this presentation. And the first question that I'll anticipate, I'll just get it out of the way, is wait, but doesn't Xen already have PCI pass-through? And yes, it does. On x86 for HVM guests and for PV guests. But not on ARM and not for PVH guests. We'll get into that. And on HVM DOMUs, we require a backend running Qemu. So PCI requests are going through Xen IOREQ and then into the backend with a device model which emulates your PCI bus and has PCI devices emulated or physical. In the PV case, it again requires a backend, DOMU or DOM0 or DOMD or running, where you have these guest special drivers, PCI back, PCI front, that are necessary, and so moving on to VPCI on PVH and ARM guests, we don't require this backend. No Qemu, no PCI back, and Xen itself is virtualizing the PCI bus. So this means Xen is trapping accesses to the PCI configuration space and mediating access to the different direct assignment of devices. Xen is handling the bar mapping in P2M. Xen is setting up interrupts, and I will also mention that some accesses are handled in Xen VPCI, and some are forwarded to the device itself. Okay. So forgive me, newer to the x86 side, but on a PVH DOM0, a PVH v2, it uses a VPCI to pass through all the devices to the PVH DOM0. We have a proof of concept with PCI pass-through to a PVH DOMU, which we intend to eventually submit upstream. So Xen traps accesses to the PCI config space, and so Xen presents a virtual I/O port to the DOM0 guest and DOMU, and this is the legacy way of x86 accessing PCI config space. The future better way is ECAM, enhanced configuration access mechanism, and this is currently is supported on an x86 PVH DOM0, and future work will enable eCam for DOM use, PVH DOM use. All right, so now let's move on to ARM. So ARM, we only have eCam. And so in Xen, we set up MMIO handlers to trap the eCam region. And that eCam region is defined in a device tree. So here's an example of a device tree that is presented to the guest with the VPCI definitions here. And yeah, so right here in the device tree, we have the range of memory that is used for eCam access, for PCI config space access. And additionally, we have spelled out right here in memory, in the device tree, the memory ranges that are valid for programming your bars, your PCI memory accesses. Okay. So how does PCI generally work on ARM? We have some ARM hardware to help us with this, including, well, so the PCIe controller or root complex. I think of this as basically a PCI to AXI converter. It's all, PCI is memory-based, AXI is the ARM memory bus. Then that PCI controller, or the AXI bridge, PCI to AXI bridge, tags the AXI transactions with some sideband data to identify the BDF of the device. And then from there, it can go out into the SoC, the system, and be routed through the SMMU potentially, or be directly accessed from the applications processing unit, the APU. We also have, for interrupts, we have some ARM hardware called the GIC v3 ITS. This is the interrupt translation service. And this allows MSIs, the message signal interrupts, to be handled by the ARM's interrupt controller. So when we bring Xen into the picture and want to enable PCI pass-through on ARM, we're going to be using VPCI. So this is the Xen component that mediates config space accesses. So yeah, walking through each component here. Let me see if I can figure out the laser pointer. There we go. Yeah. So we have a DOMU, and it is, say it's trying to access the PCI config space. Xen traps the eCam region access and either handles it or forwards it to the PCI device. And this is, so then the DOMU driver can set up the bars in the device. So that now VPCI will set up the stage 2 mappings. So when a guest tries to access the PCI device memory, it'll get translated by the stage 2 MMU in the ARM core, and then finally reach the PCI device's defined memory region. Now, when the PCI device wants to do DMA, we go the other way. We pass the AXI transaction passes through the SMMU. The SMMU can identify which PCI device it came from based on the AXI sideband data, and then do the proper P2M translation, and then the DOMU, it's available for the DOMU. On the interrupts side here, we let's start from the bottom. So interrupts, message-based interrupts work similarly to the DMA case, but it has a couple extra steps. An interrupt, the interrupt is just a memory access, which gets translated through the SMMU, and then reaches the ITS. Now, the ITS has a write-only, call it a doorbell register. So, which, the MSI message from the PCI device writes to this register. And then the ITS reads the AXI sideband data to figure out, okay, it's from this PCI device or that one, and then it can raise, then Xen has some VITS handling. The Xen knows which PCI device the interrupt came from and can inject the interrupt into the guest, finally. Okay. So on ARM, we are relying on there's two different cases, for DOM0 and for DOM0-less. So in the DOM0 case, we rely on DOM0 having a driver for the PCIe root controller. And then Linux DOM0 will scan the PCI bus and inform Xen about each PCI device that it finds. In the DOM0-less case, we have the PCIe driver, root complex driver. In Xen, it could be in U-boot or firmware. I chose to put for our Versal platform, I chose to put it in Xen because it was convenient. But then Xen can scan the PCI bus and provide a virtualized view of PCI devices to the guest. Next slide here. My newest addition. So I love playing with hardware. I haven't actually touched this board in person yet, but this is a Versal VCK 190 board, which actually is an endpoint form factor, but the PCIe controller can be configured in root complex mode or root port mode as well. So that's what we've done. And then we need this special little adapter to be able to plug in a PCI device. And I can access this all remotely. It's pretty cool. Anyway. Okay, a little bit of history, and thanks for Roger for helping me out with this slide. So VPCI back in the PVH V1 days, which we probably don't want to remember, there was a need for a way to interact with PCI devices. So, there were some hypercalls that were introduced to set up the hardware, but this required modifying the OS. So in PVH v2, which is now known as PVH, this is where VPCI was born. And please, correct me. I'm still new to this. So we wanted to get rid of the hypercall interfaces and take advantage of the hardware virtualization features and manage interrupts the native way within Xen without having to customize the OS for special Xen isms. And more recently, VPCI is useful for ARM as well. So, all right, moving on. We overcame a big hurdle recently, and again, thanks to many contributors and reviewers. The VPCI was stuck on a locking issue, spin locks. So in Xen, we have a big PCI devs lock, and it's global, right? So you're holding the lock, then basically no no other core. There's lock contention. So in VPCI, the handlers need to have a way to, not race. So yeah, if we do this with the PCI divs lock, there's contention. If we don't hold the PCI divs lock, which is not desirable, but the PDev object could disappear. So the solution was to introduce a new per domain read-write lock to protect the PDevs objects list. And it's a huge achievement. There was a patch queue of I don't know how many, 80, 100 patches that now can be unblocked. So there were some other approaches that were evaluated, attempted in a way, including reference counting, breaking the global lock into smaller locks, or changing the global PDevs lock back into a RW lock, which, anyway. So some future work, on ARM, some of these items exist in downstream branches. Some are only ideas so far. But so let me go through each one, I guess. On ARM, this one vMSI support with vgig v3 VITS. So this exists in a downstream branch, and a colleague from ARM is helping to upstream this. SMMU PCI support, again, exists in a downstream branch, and it's on my never-ending to-do list to submit another revision of this series. On x86, we need to introduce Qemu-PVH pass-through support. And again, this, to further align the architectures between x86 and ARM, that they will look more similar. There are, in VPCI code, there's some more work to enable the remaining PCI header handlers and capabilities. Currently, I'm talking about PCI capabilities here. So currently, these are defined in the PCI standard. Currently, we only support MSI and MSIX capabilities. Future work is also with SRIOV. There was a series posted to the list a few years ago. In DOM0 list, this one exists in a downstream branch as well, and is unblocked now. Last one here, the virtual device, virtual bridge device. So currently VPCI presents a PCI bus to the guest that only has endpoint devices, which here looks kind of like this. Okay, the entirety of my PCI bus is just a single device. Now, typically, most normal PCI buses have a bridge on them. So, and this is needed for certain guests to be able to properly read and scan the bus. My temporary hack is to, force Linux to just ignore the fact that we don't have a bridge device here, and that's my little magic rune that makes it work anyway. All right. All right, so VPCI and virtio-pci, we want to be able to use them both at the same time, but there are then some considerations to be made with, okay, how do we get them to work together? So if I'm only doing VPCI, then I have a PCI bus in my guest. Nice and simple. If I'm only doing virtio-pci, I have, again, a same one bus in my guest. But so one possible solution is have multiple segments, so multiple PCI segments. Now, there's a question. The main pushback for that is that we probably don't have as much guest support for that, considering on x86 we only have one I/O port, I think. I could be wrong. I don't know. But with multiple segments, there's also more MMIO and interrupts, just resources required to support that. If we do a single PCI segment or a PCI bus, then okay, we need a way to translate BDFs and make all devices fit on a single bus somehow. On ARM, this may be a issue if the PCI controller may, the AXI transactions may be routed through a DMA coherent path, or it may not be, which means, okay, does the AXI transaction snoop the caches or not? If not, then the guest needs to do some extra operations. Maybe it's more barriers or cache operations to be able to fully do DMA with the device. But if our PCI bus does snoop the caches, then all good. We just put this DMA coherent property in our device tree, and then we are coherent. For virtio-pci, we can assume that we are always DMA coherent, but not so for a real PCI bus. So, this needs some more discussion, but I hope I tried to just list out what the considerations might be here. Okay. Okay, and then DOM zeroless. All right, Stefano already talked about this, but here is Stefano's slide for review. So thank you, Stefano, for this slide. But yeah, basically, okay, for virtio-pci, we need the backend to emulate the bus. So okay, if our DOM-U is started from boot from the hypervisor, then we just have this busy wait loop until it's ready. All right. That's all. My presentation is short, so thank you, for listening here. So, what questions do you have? Please ask questions. I know you've got them. Yes.
So, could it be possible? Does Linux support multiple PCI segments?
Yes, with ECAM ranges.
Okay, then maybe it's best to go with multiple PCI segments and just assume that you're not going to be dealing with other OSs that are going to matter or support them. Is that a reasonable assumption?
Well, I would be happy with that choice, sure, but I don't know if everyone would be. Yes.
So, not really comment on that specifically. x86 has had multiple segments for years and years and years, but even in today's systems, they're still faked up to look like one for DOS compatibility.
Okay.
So the reality is that, yes, but for compatibility reasons, it's still morphed together. The first thing that truly went and broke that was Intel VMD support, and it took 3 years to get the drive for that upstream into Linux because there were fights and fights. So notionally it exists, and it's had approximately 0 testing. So infer from that what might happen when you try turning it on.
Yeah.
Stuff will break and then it'll get fixed. And Qemu machines don't automatically, so Qemu knows one precise.
They're still merged back into a single segment for compatibility reasons.
Do we care about compatibility here?
Why, probably. Okay. All right. Other questions? Yes.
Would one of these PCI implementations be like a bridge for the other one, or would that make things too complicated? We still have a single, we choose one of them to be the root, and then the other one will be a bridge on that one.
It's an interesting idea. And I don't know. So one proposed direction with the single segment idea is that Xen VPCI or IOREQ or something in Xen is the mediator of BDFs. So a virtio-pci backend device model would request a BDF. Xen would allocate it, and then that would be the BDE. Roger, yes? Yeah. Yeah. Mm-hmm. Yeah. It's separate MMIO handlers, separate entry points into the hypervisor. Yeah, currently. So, okay. Well, hey, thank you all for listening to me stumble through this. So.